Hi Spring fans, welcome to another installment of Spring Tips. I've been eagerly awaiting the chance to talk to you about today's video. Today we're going to talk about the brand new Spring Native 0.x release, which brings with it a bevy of new features, which we'll look at in just a moment. But before we get into that, I want to contextualize where we are and why we care. This new release marks, to me at least, the largest single step we've made towards Spring Framework 6 and Spring Boot 3. So if you went to Spring 1 2021 this year, then you know that our big Spring Framework 6 revision will be coming out next year in 2022. And a huge part of that is our hope to make Spring deeply and natively aware of GraalVM and GraalVM native images and AOT in general. That's a big part of the promise. There's other things as well. There's the new baseline supporting the Jakarta EE APIs and Java 17 and all sorts of other stuff. But a huge piece of that is this new Spring Native support. And I don't know that Spring Native itself will be merged. I'm not sure if we're just going to take the code and put it into Spring Framework or what, but something like it will appear in Spring Framework, right? Something that might be newer and improved by then. That's after all, that's almost a year away in some ways, but nonetheless, this is a huge part of that work, that research, that journey. So I'm really excited about that. I'm really excited about what this portends. Right now, Spring Native is an experimental and second project. It's not the same as Spring Framework itself, but it is aware of the patterns that people have when they use Spring Boot and when they use Spring Framework. And so it is a great way to take your existing applications and make it work with GraalVM. GraalVM, of course, is an ahead-of-time compiler. Or the GraalVM native image compiler is an ahead-of-time compiler that takes your source code and turns it into an architecture-specific binary that is statically linked. It's self-contained, right? These applications tend to have a much reduced memory footprint and RSS, and they tend to start up in fractions of the times that the equivalent application would start up on the JRE. It's a really exciting piece of technology, and Spring Native is going to help you fully exploit that technology to make your applications just that much more ready for production. GraalVM works by looking at your code at compile time and throwing out all the things that it determines, again, at compile time, that you're not using. The problem, of course, is that it doesn't know everything that you're doing at runtime, right? Java, for all of its stodginess and its warts, can be a very dynamic little language indeed. It can do things at runtime that you might associate more with the likes of something like JavaScript or Ruby or Python or Perl or Lua or whatever. It's got a runtime, first of all, so you can actually dynamically register classes in the class loader, create instances of them with reflection, create proxies out of them, serialize instances of their bytes to disk, hydrate those and load them up in another JVM, all without ever having a concrete reachable type. And that's impressive, right? So as a result, there's this world of difference between what the compiler can understand and what it considers to be reachable and what actually gets executed at runtime. Spring Native is how you bridge that divide with your Spring Boot based workloads, which is to say how you bridge the divide for your typical enterprise application. So we've got a lot to look at in this new release, some of which you might have seen before, although most of which I don't think so. And so with that, let's get right into it. First, we'll need to get the environment set up and running so that we can use it. We'll need GraalVM. Let's use SDKman on my Mac to find the GraalVM Java installation. You can do SDK list Java. Now, SDKman is a very convenient tool that works on all Unixy sort of modern operating systems, so Mac and Linux, and you can use it on Cygwin or WSL for Windows. And if you scroll down, you can see all the different Java versions out there, all the different SDKs, etc. You can see that GraalVM is already installed. I've already got 21.300 R17 Graal, right? If I wanted to install it, I would say SDK install Java and then the version. It's already installed. I can then say SDK default Java, and then that'll be the system-wide Java version. Or if I just want to use it for the current shell, I can say SDK use Java and then that version. And that'll set up the Java home and all that stuff for the current shell to be pointing to that. That's not all though. You also need the native image compiler. and there's a command line utility called GU that comes with GraalVM. So you say GU install native image. It's already installed, so it works. With that, we can start programming against GraalVM. All right, so let's go ahead and build a new application. We're going to go here to the start.spring.io, and we're going to build an application that talks to a database. I already have a database running. I can connect to it here. And I can see I've got a table called customer, and I've got some sample data. So what I want to do is I want to build a reactive application. Now, to be fair, I'm kind of goosing the numbers here a little bit because reactive applications are, by definition, going to be a smaller footprint and they're faster, right? They take up less resources and they tend to be very, very fast because of that in terms of startup. So admittedly, this is a fairly ideal sort of use case, but hey, that's me. I'm Mr. Idealism. That said, this isn't the only thing you can do. Obviously, with reactive programming, we want to support new architectures, but when it came to Spring Native, we wanted to make sure that everything that you can do in Spring, you could do in Spring Native. And so we have good support for all sorts of workloads, not just the reactive greenfield stuff of tomorrow, right? And we'll see some of that in a bit. But for now, just to kind of get a feel for the lay of the land, we're going to take a look at building a reactive application. I'm going to call this customers, or you know what? I'll call it reactive. That's probably easier. We want to get access to the latest and greatest version of Spring Native, which is not GA yet. But we don't even want just the RC. We want the actual milestones. Because as I record this, we're just a few days before the actual release, and so this will look pretty similar to the next release candidate that comes out. And so we're going to use 2.62 snapshot for Spring Boot. We're going to use Java 17, and we're going to bring in our Postgres support. We're going to bring in R2DBC and the reactive web support. And of course, we're going to bring in Spring Native. Now, by bringing in the snapshot version of Spring Boot 2.6.2, we automatically get the snapshot milestone repositories added to our build, and it's configured to use the Spring Native version 0.11.0 snapshot, which is what we want. Let's go ahead and hit generate, and we'll open this up in our IDE. Okay, UAO. Okay, UAO reactive.zip. All right, there's our application. First things first, notice that I'm using Java 17. The last 0.10.x line of Spring Native didn't work particularly well with the newer versions of Java beyond Java 11. And so part of that, of course, is that GraalVM itself has now released there's a version that supports Java 17, and Spring Native works against that. So I am super excited about that because it means I no longer have to have this fork in my decision making. Am I going to target GraalVM native images? No. Okay, then I can use Java 17. Otherwise, I need to use Java 11. That's no longer the case. Now there is officially no reason at all to ever use anything besides Java 17 or newer. And that, by the way, is our stance on it for our applications today and going forward, right? If you are using Spring Framework 5.x, then of course we still support as far back as Java 8, but going forward, the new generation of Spring Framework 6, that will be the foundational layer will be based on Java 17, right? And that in turn will inform the baseline for Spring Boot 3. So let's add some types here. This will be a record, a Java record. I'm going to create a repository that uses the reactive CRUD support, customer integer. And we're going to create a functional reactive HTTP endpoint to serve up the data. So router function server response turn route. Good. Customers new handler function dot build server response dot OK dot body, and here I'm going to return data by talking to our functional, our reactive repository rather. So we'll say repository.find all, and the type of the payload is customer.class. Good. So there's this, and there's that. So that'll do. That should be enough. We need to connect to our SQL data store, of course. So we'll go back to the property file, r2dbc URL, r2dbc colon postgres localhost bk. Username is bk. Password is bk. Let's see if this works. Let's just run it locally on the JRE. Okay, up and running. Customers, et voila. Seems to be working just fine. Good. So there's our trivial application. It's doing fine. Let's turn this into a native image. So what I'm going to do is I'm going to go to the command line, and I'll use the Maven plugin that's already been pre-configured for us. Right? You can see that here. The plugin with Spring Boot Maven plugin, with Spring AOT Maven plugin. We've also got build pack support. You know that Spring Boot can automatically create a Docker image for you. You just use Maven space spring-boot build-image. Well, we've pre-configured native image support as well. So if you should so decide, you can actually have Spring Boot create a Docker image in which you have a Linux architecture-specific binary of your application, a GraalVM native image. So it's a GraalVM native image in a Docker image, and you just do Maven spring-boot build image. That's super convenient, right? This AOT plugin is very important. This AOT plugin you've probably seen before if you've used Spring Native. It's a clearinghouse for code transformations that we do against your code base. And at the debut, at the onset, it was fairly limited. We did a few transformations on the code before we passed that code onto the GraalVM native image compiler, but they were not substantial. As we'll see in just a bit, 0.11.x is a huge stride forward, a huge leap forward, right? In terms of what we're able to do with the AOT Maven plugin. Beyond that, we've got all this, and of course, down here we've got a Maven profile. So if you just want to build an image, forget about Docker for a moment. If you just want to build a native binary on your local Mac or Linux or Windows machines, then you can just run this package, the Maven package command, with the Maven native profile. So I've got different, I've got test support. I've got the GraalVM native image Maven plugin, all the usual stuff. But that's all pre-configured for you. So let's go ahead and now build this application. I'll say Maven skip tests. Just, you don't have to. You can actually, that's one of the nice things about the Spring Native is that we actually support compiling your test code in a native context and then running it in that context. So you can actually create native JUnit tests, run them, and make sure everything works there. And have a sense that what you're going to do at runtime also works, in your test code. So Maven skip test equals true, and then -p for profile, clean package. Let's go ahead and run this. All right, the application built in 2 minutes. Let's go ahead and visit the target directory and see what that gave us. We can run the native image here just by hitting reactive. And there we have it. Our application starts up in 67 milliseconds. And by the way, sometimes that number can change depending on, your operating system and the entropy in the universe and what all. But either way, really fast. And what's also interesting is that it took very little time to compile. Okay, so now you've got a feel for what's possible here, right? We've successfully built an application and compiled it using Spring Native 0.11.x. The new AOT engine is a huge part of the reason that Spring Native is so amazing. It's a central piece of infrastructure through which all your code passes. The AOT engine looks at your Spring Boot application and transforms your code in such a way as to be more amenable to the GraalVM compiler. It also produces the hints that are required for the code that isn't yet optimized to be passed into the GraalVM compiler so that it understands the things that you're trying to do, like reflection, like serialization, like proxies, like loading resources from jar, class paths, and so on, so that it works in GraalVM. When you compile your application, we want to get as much information about the behavior of your application and the relationships of the objects in the application context as possible. One way we do this is by running your application. We don't actually start the application context, right? But we do register all the beans. We start up an application context with all the bean definitions registered. This gives us a chance to see the relationships of these different objects and to make it easy to understand how they relate to each other, what their configuration looks like, what their shapes are, what dependencies they have, etc. We can then use this information that we collect by running your actual code to then inform the generation of hints and transformations. Some of the transformations that we do are fairly straightforward. For example, we have a text file called spring.factories, and this text file is used most famously as a service loader for Spring Boot. So you might know that in Spring Boot and in any of your jars, in any jar on the class path, you can have a meta-inf directory with a text file called spring.factories. Spring Boot will detect the presence of those files on the class path through its service loader mechanism, and it'll evaluate, it'll instantiate and then evaluate the conditions on all these different Java configuration classes. This is how Spring Boot, so dynamically is able to register and contribute objects to the object graph. These configuration classes are just Java config classes. They have beans, they have conditions. One of the conditions that you can see here is conditional on class. Spring Boot will not register this class unless this type called cache manager.class is on the class path. So there will be no cache auto configuration if there is no cache manager.class. Well, that's something that we evaluate normally on the JRE at runtime by starting up the application and then looking at the very dynamic class path of a typical JRE application. Well, in the GraalVM native image world, there's no such thing as a class path. You can't swap out one jar for another after it's compiled. It's a statically linked, self-contained binary, right? That's architecture specific. There is no more class path. And so we can foreclose on the possibility that will be swapped out. We can just say, hey, it's not here right now, therefore it'll never be here. Because once we're done with compilation, that's it. No going back, right? So we can pre-compute that condition at compile time. And so we do. We actually pre-compute that condition at compile time, and we generate a Java class that contains the result of that pre-computation. That Java class is static spring factories.java. And it's what you think it is, right? It's a new version of spring.factories, but sort of reified as Java types. And we've configured the Spring Boot running under AOT to consult this and not spring.factories. This is not just for your code, it's also for all the code that gets contributed to the running application. So here's the result of all the auto configuration, right? We have a reactor server resource factory, and that in turn has the following type with the following, factory method and so on, right? So very, very, very powerful mechanism. This is quite a leap forward. This ability to transpile your configuration into functional configuration, and the results speak for themselves. They're amazing, right? The applications are much faster now in compilation and so on. Here, the native image compilation process invoked the AOT infrastructure, and that's how we got all this code. You can go short of a full native image and run the AOT transformations manually. So here I could say Maven Spring AOT generate. The Maven plugin is what actually generates all these transformations. So we can actually see all that without actually having to do the full native image build. And it's not just the native image build that benefits from that. You can actually run your Java code in the JRE using the AOT infrastructure, and that actually has it has the effect of reducing the resident memory footprint of the running application just a little bit. Maybe not a huge amount, but still, it's there. It's free performance, and it'll contribute to the startup time as well. So, Java -jar reactive 001 snapshot. So we're going to run this without enabling the AOT infrastructure. We're going to run it on the JRE. All right, so we ran that. It's fine. It starts up in 1.8 seconds. It's 2.28 JVM time. Okay, good. So 1.8. Okay, almost 1.9. Now we'll do Spring AOT equals true, and you can see it's 200 milliseconds. That's not nothing to sneer at, right? And you can see there's the telltale sign. This application is bootstrapped with code generated with Spring AOT. You would see this also say disabled when it's not enabled, right? When you run it without Spring AOT being involved. So Spring AOT is a win because you can actually pre-flight what your native code is going to be compiling and running with. You can actually benefit from it even if you're not using GraalVM. It's just a win, even in performance. So it's just a good thing to know about all around. All right, I've got 3 sample applications. The first is just a traditional, typical Spring Batch application. It is a job. Spring Batch is all about sort of long-lived, sequential data access-centric jobs. And so I have a job that has one step. That step is defined as having a tasklet. All I do is I print out hello world. And I'm not doing anything special. I just got this. The only reason I've got this is for my test. What I want to do is I want to run all these applications and let them run for a second and then capture their memory footprint, right? So in order to do that, the process needs to still be running. Spring Batch, absent some other thing, will start and then stop, right? So when you start up the application, it'll start the job, and then when it's done, it'll finish the job. And if there's nothing else to keep the context open, the application and the JVM just shut down. So I'm keeping the thread open, right? I'm joining the current thread so as to keep the JVM running. All right, so just a typical Spring Boot, Spring Batch application. Nothing special here. No config. I'm using H2 for my SQL data store access. So I've got an embedded database here. I've done nothing to the build. It's just stock standard, release candidate stuff. I'm not even using the new stuff. I'm using the release candidate here. Java 17, Spring Native, all that. All right, I have a reactive application. This is a stock standard reactive web application. It's a application that when it starts up, we write several records to the database. We have a functional reactive HTTP endpoint, a record, and a repository. That's it. Again, same as you've seen this before. This is nothing special, right? I've got the schema here if people want to create their own schema on their own database. In this case, the database I'm using is Postgres. And so, I've got that on the class path here, Spring Native, H2 embedded. Oh, this is H2, but the other one was Postgres. You saw the one with Postgres. Either way, it doesn't matter, right? They're both SQL databases. So this is actually a little bit more involved in that we're creating the database in the application itself. We're embedding the database in the memory of the compiled application as opposed to just a client that connects out to some other database. So in that respect, it gets a little bit slower, right? It could actually be a little bit slower than the Postgres one. We also have a traditional application. And this is, when I say traditional, that's my euphemism for stuff that I wouldn't write today if I had a choice, but I can appreciate that a lot of people still do. This is a JPA, Tomcat, servlet API based API. So here's a regular HTTP servlet based Spring MVC controller. I'm just injecting the repository and returning all the records. I've got a JPA entity. This is like it's using Hibernate behind the scenes. So I can't use Java records because Hibernate and JPA don't support it. I've got a repository. Now, again, for any other Spring Data module, such as Spring Data, Spring Data R2BC, I can use records. This is a lot more verbose. Even though I'm using Java 17, it's a lot more verbose for that. But okay, so this is going to be your slowest application. There is a lot of stuff happening in Hibernate. It is absurd, right? And it's also the least scalable of the three because, of the two, certainly between the reactive one and this one. This one will handle the fewest requests because there's synchronous blocking I/O. Right? So it's a little bit more involved, but it's pretty representative of a traditional typical application. And again, the build is just stock standard. Go to start.spring.io, generate a new project, use Spring Boot 2.6.1, use the RC1 for Spring Native, and bring in WebMVC, Spring Data, JPA, H2, etc. Okay. Let's look at some of the numbers. We've looked at 3 sample applications that demonstrate non-trivial use cases. The batch application, traditional Hibernate, Tomcat, servlet-based applications, and reactive applications using the more modern Spring Webflux and R2DBC and so on. And I've got a little script that I use called measure.sh that runs the JRE version, the AOT version, and the native version of those 3 applications and measures both the startup time and the resident set size time. The AOT version and the native version are, of course, faster, but the native version is going to be dramatically faster, right? Obviously, that's what we're here for, is we want to take advantage of that whole paradigmatically different approach to memory management and speed and startup time. But that said, the AOT engine can be remarkable in of itself. Even if you're running on the JRE, it can do some very interesting things. You can actually lower the footprint and shave off whole seconds, for example, in the case of the traditional application, from your startup time. For more typical applications, such as those I would write in 2021, it still manages to shave off, let's say, 200 milliseconds here and there. That's not nothing, especially in your dev cycle, rinse repeat cycle. When I write code on my laptops these days, it typically starts up in 1 second, 1.5, 1.3, something like that. So if I can shave 200 milliseconds off of that, that's great. I'll take it. Thank you very much. So I love the new AOT engine, and the numbers speak for themselves, both in terms of how the JRE version of the application runs with AOT enabled and how the native application runs with the benefit of the AOT engine in place. Let's take a look at some of those numbers. You can see here that the reactive application, when it's run in native mode, starts up in 61 milliseconds and has a resident memory size of 57.8 megabytes. 57 megabytes, right? That's an application with a web server and a database client, and I think maybe the actuator, whatever, I'm not sure, but very, very, very small application. The JRE version of the same application starts up in 1.7 seconds. I would remind you that I'm screen capturing as I run these tests, so things are going to be a little bit slower there. And it has a memory footprint of about 472 megabytes. That's, a far sight better than it was for typical applications on the in the enterprise, let's say 10 years ago. But yeah, that's a lot, right? If you can run a service in less, why wouldn't you want to, right? So what about the AOT version? Well, the AOT version of the reactive application starts in 1.5 seconds, right? So almost 200, actually just about 200 milliseconds that got shaved off there. And it takes 493 megabytes of memory. So it actually, in this case, balloons the memory footprint a little bit to use the AOT engine. But it shaves off a considerable amount of time in the startup. Okay, now what about going back to the traditional use case, the pendulum swing in the other way to the least efficient stack that you can use today, using something like Hibernate and the servlet stack, right? Well, in that scenario, the native application starts up in 155 milliseconds, so 155 thousandths of a second, right? Almost a tenth of a second, a little bit more than a tenth of a second, right? That's awesome. And it takes about 127 megabytes of RAM. So, more than twice as much RAM as the reactive one at runtime, and well past more than twice the startup time, just for using Hibernate and all that, right? So if you can avoid it, maybe you will, or maybe you should. The JRE version of the application takes 3.6 seconds to start up, and it takes 649 megs of RAM to sustain. The AOT version dwindles down to 2.8 seconds to start up. So again, almost a full second faster for the traditional application using AOT. And the memory footprint is about the same at 647 megabytes. The Spring Batch application, the native version of the Spring Batch application, starts up in 65 milliseconds, so 65 one-thousandths of a second. It has 83 megabytes of memory, so again, 2/3 or 3/4 of the traditional application. The Jerry version of the application starts up in 1.3 seconds and has 460 megabytes of memory. So again, 460 compared to the 650 almost for the traditional application, right? Almost 200 megabytes less just by using something like that, right? Now, obviously, batch versus web, these are different use cases altogether, but for lots of workloads, you can expect numbers that look like that for messaging, for batch, for data, for these kinds of things. The only thing I think these numbers are more typical. The traditional application with Hibernate and the servlet stack, that's going to be more atypical, okay? All right, the JRE version, as we say, is 1.3 seconds, 469 megabytes. The AOT version, 1.0066 seconds, so 200 milliseconds there, and 419 megabytes of resident memory. So there, call that 420, that's 460. We saved 40 megabytes of RAM just by using the AOT version. That's a big difference if you're measuring in terms of 500 megs, right? That could be an eighth of your footprint saved right there. So Spring Native does a lot for you, and a huge part of that intelligence comes from the AOT engine. The AOT engine has a lot of built-in smarts to help you get the most out of your Spring applications. But what if it's not enough? Well, Spring Native, like all of Spring, is a framework. It's open for extension, but closed for modification. Now, of course, strictly speaking, that's not exactly true, is it? Spring is an Apache 2 licensed open source project, so of course you can get the bits and recompile and change and do whatever you like without telling us or contributing back to your heart's content. But the point is you don't need to, right? It's got well-known extension hooks or extension planes that you can use to override the default behavior to make Spring do what you want it to do. And the same is true for Spring Native. Right? You don't have to recompile Spring Native to get Spring workloads that Spring Native doesn't understand to work well. So in this section, we're going to look at some of the extension points that Spring Native gives you, including type hints, which are annotations that you can add to your code as a start, native configuration, native bean configuration processors, and native bean factory configuration processors. Let's get right into it. We've looked at the basics here. We've looked at how to use the new Spring Native release. We looked at how to build an application and get it compiled with GraalVM. We've looked at the AOT infrastructure and some of the implied benefits of that and some of the ramifications for more or less typical kind of workloads and use cases. Obviously, there's a good deal, many more, but you'll find that the list of supported technologies in the Spring ecosystem is vast and growing day by day, right? So we have, for example, much of what you can do with Spring Boot is well supported. Lots of Spring Cloud is well supported. And obviously the list expands every day. And it gets easier and easier to create and add to that list. Part of the reason we have to have a list, however, is that it's not guaranteed that it'll work. Remember, Spring Native can do a very good job of adapting code that Spring knows about. If it's just a regular object that you've declared or a regular bean or it's something that is in an auto configuration, assuming there's no funny business, things like reflection and loading resources from a jar or proxies or serialization or anything like that, assuming that there's none of that sort of more esoteric kind of stuff going on, then GraalVM and Spring Native should just be enough, right? However, sometimes there are things we need to do that go beyond what the Spring Native infrastructure and the AOT infrastructure can understand deterministically at compile time. So for example, let's say you have a bean method that returns a type, and that type is an interface. Okay, well, that's still not necessarily enough to be a problem. But what if that interface, the implementation of it, is actually a proxy? Well, now you've got an issue. You've got to tell Spring Native and you've got to tell GraalVM about this proxy. What if it's a Spring CGlib proxy? Well, of course, GraalVM itself has no notion of this, so you definitely need to tell Spring Native about it. What we're going to look at in this section is the support for those kinds of extensions. So let's go ahead and go to the Spring Initializer, and we're going to build a new application. As always, I'm just going to call this extensibility, and we're going to use Java 17, and I'm going to bring in Spring Native, and that's it. So we're going to open this up in our IDE. So we're going to build a simple example here. Okay, we're going to say, we're going to have a bean, and we're going to create bean that returns an interface, an implementation of an interface. So let's say it's customer service, all right? And the customer service has a find by ID method where it's an integer ID, and the ID is a customer. So, let's say integer ID string name. All right, so very, very trivial, very, very, plain kind of thing. We could create an implementation and there's no problem, but for whatever reason, we're using a proxy, okay? So we would say var cs equals proxy factory dot get proxy, and we pass in the proxy interface, which is customer service.class, and we'd return a new method interceptor. So if you've ever used Spring Framework's ALP support, then you've probably seen this before. It's not all that new, and what's happening is we are simply intercepting method invocations. It's going to create an implementation using JDK proxies of this interface, and we get to register a callback, a listener, an interceptor that gets invoked every time somebody calls a method on that implementation. So as an example, we can return a application runner that injects a customer service dot find by ID 1. Okay, so I'm going to say find the ID, and we're just going to print out the result. All right, so there we are. So it's going to call a find by ID, but of course, something needs to actually happen when you call find by ID, and that's this callback. So we're going to say if it's like JavaLang, Boolean equals, or JavaLang, JavaLang object Boolean equals, or JavaLang object to string, or hash code or whatever, all that we don't care. We'll just return null, which is not great for collections, but that's not what we're trying to demonstrate here. So we'll leave those cases uncared for. But if we're trying to call, let's say find by ID, well, in this case, I want to return a new customer, and it'll just be number 1, and it'll be Dr. Sire. I don't know, whatever. Okay, so now let's see if that works. Okay, we'll make this a lambda, and it's just a trivial example here, right? All I'm doing is I'm creating a proxy. Not something you are likely going to do in your code, but you can kind of understand why this might be complicated. So we're going to run it on the JRE first. There you go. Got the record back when I printed it out. So it worked. Our proxy worked, but this isn't going to compile well. And the reason is because we're creating a proxy, and that proxy doesn't look the way we think it looks, right? If we actually say cs.getClass.getInterfaces, and then do for var I in this, and we do system out I.getName, what do we get? Alrighty, so we ran that again. You can see there's actually 4 interfaces here, not just the one that we created, but 3 others that are, part of the proxy process when Spring, the mechanism we use to create these proxies for you. So we can tell Spring Native about it through the type hints mechanism, and there's a whole slew of hints that you can use here, right? I've got native hint, and this is great for if I want to register JDK proxies, I have to say JDK proxy hint, and then here I've got the types. Okay, well, what types? I have to actually add commas and dot classes, so I'll say dot class comma. All right, and then that goes there. There we are. Okay, so there's my JDK proxy hint telling. Oh, did I forget to add the comma? Good. So this is my JDK proxy hint telling Spring Native about the interfaces in the order they appear. That's very important, right? It has to be in the same order. So JDK proxy hint is going to make the difference. So let's compile it and let's run it and see what we get without this. Okay, we'll do a native example. So Maven -d skip tests equals true -p native clean package. All right, so there's our application. Let's go ahead and check out the result. So extensibility, it fails, right? is not happy with what we did. It said proxy class defined by interface, blah, blah, blah. Proxy classes need to be defined at build time by specifying a list of interfaces that they implement. So this is a JDK proxy. It uses just interfaces. Spring has support for another thing called an AOT proxy, which actually we subclass concrete classes. We don't just create implementations of interfaces. We can actually enrich or apply aspect-oriented, cross-cutting kinds of concerns to concrete classes. Why is that interesting? Well, it's interesting because GraalVM doesn't know about that, right? And so you have to be aware there's two different kinds of proxies in the Spring ecosystem: regular, good old-fashioned JDK proxies, which are limited to interfaces, and also AOT proxies. But the mechanisms, the use of these annotations is the same. So let's now add this back and rebuild. Okay, there's the application. Now we try again, and it worked, right? All we had to do is to register that little proxy hint telling it about this, and then GraalVM did the rest. And so that's what Spring, that's the power of Spring Native, is you can easily add these hints for things where Spring couldn't deterministically figure out what you're trying to do. Spring doesn't know that inside the body of this method, you're doing some of this, funny stuff, right? It doesn't know about that. Now, are you statistically likely going to be doing something like this? No, probably not, right? Again, Spring does a fair bit of this kind of stuff behind the scenes, and we make sure that we have hints for the respective frameworks like Spring Data and things like that. But it's just useful to understand why that's there. And there's a number of hints that you can use, right? I looked at JDK proxy hints, but there's also AOT proxies, as I say, and that takes an AOT proxy hint. You've got hints for resources, like if you want to load a file, you can say this is a class path resource. Maybe I'm going to load this file from the class path or something like that, so I can actually register that. There's we've got serializable hints. We've got hints for you can provide a trigger. You can say, okay, this type this hint should only be evaluated if this type is there. Or more usefully, you could put like what's a environment, some sort of auto configuration. So let me see, auto configuration. You could put whatever on the if this is present, if this auto configuration evaluates to true, then and only then does this hint apply. So you can do all sorts of things to make this hint more robust and to encompass more things. And you can have like, I'm going to register this serialization hint and this resource hint and this proxy hint, but only if this class, this auto configuration is active. Okay, so very cool, right? You can have as many of these as you want. You can have native hints upon native hints, or you can use the umbrella type like native hints. And you could say native hint. It's just an array of native hint, right? This is very useful. If you're going to do the most useful one I use on a daily basis, or not daily, but certainly a lot, is the type hint. Okay, so type hint. Here you can specify the types you're going to use for reflection. So let's say you were going to reflect upon a type, right? And it's a type that's already known to GraalVM. It just doesn't know that you're going to reflect upon it because maybe you're doing something with a string version of it or whatever. And here you can actually specify type equals customer service.class, and the access that you want people to have, you specify in terms of access bits dot, right? So this is the old thing. So access bits dot all, for example. Now this has actually changed, this bit right here, the access bit. So let's go back to the initializer and let's make sure we're using the latest and greatest. We'll hit explore, copy, and paste all that in there. Okay, so now you can see this no longer works, but now you can understand why that was there, what that was before. Now it's something called type access, and you have a lot of options here: auto detect, declared classes, public methods, queries, resources, blah blah blah. Right? Resources, if you want to load the type as a resource from a jar, that's it. You just want to literally load the type, the class file from a jar, for example. If you want to enumerate all the declared classes or all the declared fields, whatever, or just do auto detect. So this might be very common. You might see this a lot, particularly for framework code that isn't Spring, right? If you're using Spring, but you're using some other thing with Spring, and Spring doesn't know about that, then you might find yourself using type hints a lot. All right, so we've met the new version of Spring Native. It has a lot of really interesting possibilities, but if we want to go further, we need to bring in the Spring AOT framework as a dependency. So go to the build, add AOT, Maven, reload project. Okay, so first things first, you've probably met the native configuration mechanism in earlier versions of Spring Native. So that still works. So extensible native configuration. What you may not have done before, what you may not have seen before, is that we can actually just create this in the same jar as our application now. It's no longer fed into the class path of the Maven plugin itself. It's just part of the class path of the application, just like auto configuration and so many other things. So we're going to implement native configuration, and the contract here is very simple. You're given a registry, and you can programmatically register types. So maybe I wanted to create a native entry proxy for those interfaces that we looked at before, right? Here we go. There we go, good. I want interfaces. All right, so there's that. And that's programmatically registering my types. Now, of course, in order for this to work, I have to create an entry in the Spring.Factory's service loader mechanism. So we'll say meta-inf, a new file, Spring.Factories. So now we need to register this in the new text file. Let's the key is the type that we're implementing. So copy this reference equals, and then the type is this one here. So copy that reference, that, right? Good. So there's my native configuration type, and we can see that it's running. We'll say system out running inside extensible native configuration dot get name. All right. So let's see what this looks like. And remember, we've commented out the hints here, so they're no longer there, and yet we should see the hints still contributed. Now let's compile the application as before. Okay, so there is our type. That's worked, right? And you can see we don't have those hints anymore. When the application was compiling, way up here, we would have seen that we're running in, that type. So let's see if we can find that needle in the haystack. Let's just do this. There you go. Running inside, common example, extensibility, extensible, native configuration. So it got picked up, and it was given a chance to contribute the hint, and that made the difference, because without this and without those annotations, as we saw before, the process would have failed. So good. So this is very useful, but this is also very low level, right? What you're dealing with here is a registry, and you have access to the code, but really you don't know what types you've got there. You don't know what you're dealing with. So it's not great. This is fine. It was the old way, but there's a better way now, right? And that is, you can create a type like this. You can create extensibility or extensible native. Okay, so it's a B native configuration processor. That's this thing right here, right? And I just called it extensible B native configuration processor. And to make that work, you get a callback method. Now, this is not our favorite, most recommended way, but it can be useful because you are given a chance to sift through each object in the application context. So I can say, give me the injection points, give me the user instance creator, give me the user bean class. I can just get the name here. So let's say system out extensible bean name native configuration processor get name. Okay, and run this, and there we go. Okay, so I'm going to print out that we're inside this class, and that we've got this type that we've discovered from that's being contributed to the Bean application context, I can just basically inspect every single type, right? Which is useful, right? It's very useful. I can actually look at the properties. That's to say, the Java Bean properties, the setters, that kind of stuff. I can look at the injection points, which is where this thing is being used. It's very useful. But this is a sort of one bean at a time approach to working with the system. And maybe that's what you want. Maybe that's enough. And you still have access to the registry as well. So you can say registry.proxy, serialization, JNI, initialization, reflection, all that kind of stuff. You can do that as well. Let's register this type just as we did before, again, here in Spring.Factory. So the type, as before, is the name of the interface. And the value is the name of the implementation. So there we are. Goody. Okay. Good. So there we go. There's my new contributed thing. Let's go ahead and rebuild this. Okay. So it worked, of course. Nothing has changed for the presence of that particular interface. But let's look for this. Right, there you go. So you can see we're given a chance to work with every bean that's being created. And so if you want to use that information, if you want to inspect the properties or the return values or anything like that, you can do so easily. Now, but again, this is it's a one bean at a time approach. The final and my preferred, I think all of our preferred way to build integrations is to use the Bean Factory native configuration processor. So we'll create another one here. Extensible Bean Factory native configuration processor. Whew, these types don't leave a lot to the imagination. But that's okay. There's not supposed to be an imagination here. It's supposed to be very clear what you're supposed to use. So there you go. Implement that. All right. So there's our last type. And now you got access to the whole application context. You have also got access to a type of registry, right? To the registry. So let's go back to our code and let's go back to the type system, the native configuration version rather. And let's just drop this out. Okay, there we go. And let's re-implement it here instead. What I want to do is I want to go and look for all implementations of something, or maybe I want to find the bean in a certain way. So I can say beans with annotations. Okay, so I could actually maybe I could have an annotation on the type. Maybe it's a marker annotation, right? Just any old annotation. It could be at customer service. It could be a qualifier. It could be at component. It can be anything. Just any arbitrary annotation, and that way I could find all the instances, right? Or maybe I want to just inspect all implementations of that interface. In this case, I've only got one, but let's say I do get beans of type customer service, right? So whoops, not CSS, service.class. And that gives me back a map of bean name to type, right? And I can say, okay, beans of type for each K and then the bean. And now I can actually just iterate over each one and programmatically register that type. Okay, so here's my, maybe I have maybe it has other interfaces, so I can actually get the bean. I can say bean.getClass.getInterfaces and go through all that. But we know that Spring proxies automatically create these three, and we know that there's only one instance that has customer service. So in this case, it's the effect will be the same. I'm just registering one instance. But this is very interesting because now I have full access. I don't need this anymore. Now I have full access to the application context, right? So you can imagine all sorts of use cases. In fact, this interface is used in lots of places in the Spring native projects, right? So for example, repositories, right? Spring Data repositories, you can see we actually have a fair bit of logic here to make sure that we programmatically register the interfaces for each of your Spring Data repositories, right, including these common ones and so on. So, we use this a lot for all the sort of stuff that we're doing in Spring Native itself. Let's go ahead and register this with our Spring.factories, just as we did the other one. So here, it's a bean factory equals, and the type here, copy reference. All right, goody. There you go. So there's our bean factory native configuration processor. And that's the final piece. So let's print out where we are. So system out running inside extensible bean factory native configuration processor dot get name. Goody. All right. So remember, we don't have any other hints anywhere else. We don't have it here. We never did. We don't have it here. We don't have it here anymore. Clean that up. So it's just here. So we're hoping that it'll find the bean of type customer service, and that we'll be given a chance to register the hints accordingly. So let's try this. All right, it's worked. Look at that. There's our application. We have our proxy. We have our interface-based proxy. And it has worked, right, as we expected it to. So these different mechanisms give you different access to the application context. I would use Bean Factory native configuration processors for just about everything, unless you're dealing with something that lives completely and utterly outside of Spring. It's never registered in Spring. It's never a part of Spring. In which case, you might want to just use a native configuration interface. The native configuration interface also has the benefit of being the right place to stash those annotations. So we saw that I had annotations on the application itself. Those annotations can also live on a native configuration interface as well, implementation. So if I put those here, those will get picked up and they'll be applied to my code base, right? So in this case, I can reuse those annotations. I can reuse those hints by packaging them in a native configuration and then adding that to the class path of some other module, and they suddenly benefit from these hints. So maybe you don't need to programmatically register your hints. You can just use the annotations on the native configuration type. So with that, we've looked at how to extend Spring Native and how to extend its understanding of your application. You shouldn't need to do this, but if every now and then it happens, at least you have the tools in place to make it easy. GraalVM is an amazing opportunity. It represents a way to take Spring Boot applications into new categories, new horizons, new niches, like, for example, infrastructure. You can take an application and write something that controls Kubernetes, for example. Right? You can actually build Kubernetes controllers and operators and so on using Spring Native. I even built a set of Spring Native hints for the Kubernetes Java SDK. Think about the possibilities there. You can write Spring Native code to control the way it manages and works with your Spring Boot applications, which themselves could be Spring Native based. And speaking of Kubernetes, GraalVM changes the whole discussion around what it means to be cloud native. If you choose Spring Native in the Spring Initializer, then it'll pre-configure build pack support for you. Build packs are, of course, a great way to take an artifact, an application artifact, be they a .jar, .NET.exe, or Ruby on Rails app or Python app or whatever, and turn it into a container, a Docker image that you can then deploy into your cluster. You can easily get a GraalVM native image inside of a Docker image just by saying maven spring-boot:build-image. And then you can deploy that newly built container to your Docker registry, the VMware Harbor, Docker Hub, Google Container Registry, or whatever, just as you would any other container. This is a great way to take applications to production on something like Kubernetes. It's always wonderful to be in production. And now, thanks to Spring Native, it's less expensive too.